Yeah, maybe just to adhere to the schedule. Without further ado, let's get started. So yeah, welcome everyone to our second edition of the library workshop, known for video understanding. This is really the first time of such a hybrid format for us, so we're still trying to figure out many steps. There might be some issues, and please let us know if we encounter any. But it's super exciting. And known for video is a broad problem requiring actually all of us as a community to tackle it. It has sub-problems like video backbone design, segmentation in space and time, long-term modeling, multi-model, instructional video, etc. So today we actually have 3 invited talks, each half hour, and then after a short coffee break, we have the second part of today's workshop that will be centered around 3 important competitions for better understanding the long-form videos. And we have the invited winners to tell us about their solutions. I hope you will enjoy it. And I think right now it's 10 o'clock. So without further ado, let's kickstart. Let the show begin. Our very first speaker is Liming Wang. Liming, you are here, I guess.
Yes, can you hear me?
Yeah, we can hear you.
Okay.
Maybe if you can do some kind of configuration, I can introduce you.
Okay.
Maybe I need to stop my screen sharing, or I don't know, like you can.
Yeah, so I can share my screen, I think.
Sounds great. Yeah, so Li Ming is a professor at Nanjing University. He's an expert on video understanding, object checking, etc. He won so many first places in challenges like ActivityNet, Kinetics, and specific to long-form video understanding, he also has a CVPR 2022 paper on generic event boundary detection.
Yeah.
So his talk will be 25 minutes long with 5 minutes Q&A at the end. So for the audience, if you have any questions, if you are in the conference, maybe you can just raise your hand. And if you're in the Zoom, you can directly type in the chat channel and we will attend to that at the end of the talk. Maybe let me stop my sharing and maybe you can maybe share your screen.
Yes. Okay.
Yeah.
Yeah. It's fine.
Yeah, looks perfect.
Yeah. Okay. So I think I should say good morning, I think. And my name is Niming Wang, and I'm from Nanjing University in China. And thanks for inviting me. And today I'm going to talk about our recent works on efficient and deep video action understanding. And here is the outline of my talk. I think first I will introduce a very brief introduction to the video action understanding. And then I will introduce our works on efficient action recognition. And after that, I will introduce a video MAE, I think, which is a data efficient learners for video self-supervised training. And finally, I will introduce multi-sports benchmarks. Okay, so what is action recognition? I think simply speaking, and action recognition is to recognize what's happening to the actors in this video. Let's say playing basketball or riding bike. And in fact, I have been doing research in action recognition, I think for more than 10 years. When I was a fresh PhD, we're doing action recognition in the lab, which means the videos are relatively simple and are captured in a clean background. And then we move to action recognition in TV and movies. And these videos are with high quality, but the action classes are more complex. And recently, I think we focus on action recognition in the web videos. And these videos are easily connected, and we can build very large scale benchmarks like kinetics. And normally there are several action understanding tasks. I think the most simple one is action classification. And in this case, we are given a trimmed video, and our objective is to classify each video into a predefined category. And the second one is temporal action detection. And in this case, we are given known and untrimmed videos. And we need to not only recognize action classes, but also we need to detect the temporal interval of each instance. And the third one, I think, is spatial and temporal action detection. And in this scenario, we are given videos with multiple actors. And our objective is to localize each actors with bounding box and recognize their classes. And of course, there are other tasks like growth action recognition, abnormal action detection. And in recent years, I think video and language understanding is becoming more popular, and like video retrieval and video grounding. Okay, next, I think I will give a quick overview to the history of deep networks for video action recognition. I think the most successful network is two-stream CNN, which it was proposed by Oxford at NIPS 2014. And it is composed of a spatial network and a temporal network. The spatial network is for static image feature extraction, and while the temporal network is for motion information extraction. And it is operating on an explicit motion representation of optic flow. And I think it is the first work to achieve very competitive performance to the handcraft features like improved trajectories. And later, I think in 2015, Facebook introduced the large-scale 3D CNN. And here I want to say it should be noted that 3D CNN was not invented by Facebook. In fact, it was introduced in 2010. I think it is earlier than AlexNet. And this work demonstrated that large-scale supervised training can enable 3D CNN learn effective spatial and temporal features. And these features could be successfully transferred to downstream tasks. And later in 2016, and I think our group and with colleagues from CUHK and ETH, we proposed the temporal segment networks. And previous two networks are mainly focused on short-term information. However, we think for some action classes like high jump, we need to capture long-range temporal structures. So we propose an efficient, I think, temporal sampling strategy called segment-based sampling. We first divide the video into several segments, let's say 3, and in each segment, we pick a frame, and we perform CNN on all sampled frames, and we fuse their predictions. So our network is a video level architecture. We can capture long-range temporal information. And later, I think in 2018, CMU and Facebook proposed a non-local network, and it basically uses self-attention operations to capture the global dependency among pixels. And their experiments indicate that this flexible self-attention is an effective feature learners, and their results show that they are better than the 3D counterparts. So here is a very brief overview to the previous network backbones. And next, I will introduce our efficient action recognition networks. And as we discussed, and there are two kinds of networks. One is two-stream, and the other one is 3D CNN. However, these two networks have their shortcomings. So our basic idea is to whether we can keep a good balance between accuracy and efficiency. And we think we can build a network mostly based on a 2D CNN, and then we can insert very small number of temporal modules for temporal information capturing. And this is our basic motivation. And we observe that the motion information are quite small, and also the pattern very complex. So we need to consider a kind of explicit and adaptive temporal modeling, and with self-attention modeling. And in addition, I think this strategy also share two other advantages. The first one is we call it no computational cost, because most network is 2D-CNN. And the other one is we can benefit from some successful in 2D-CNN, and we can use the ImageNet training to accelerate our video network training. So our first work is temporal adaptive modeling, which was published in ICCV 2021. And our motivation is that we observe temporal information is quite complex and diverse. So we think we need to design a new and adaptive temporal modeling strategy. And we specifically consider a two-level modeling strategy. And here in this figure, I think I show the basic idea. And in this figure, I think the most simple one is temporal convolution, which use a fixed kernel for all videos. And the second one, we can see we can learn a temporal attention maps to learn a video adaptive attention weights. And however, we think these two methods maybe have their own shortcomings, and we think we can propose a two-level adaptive schemas. One is temporal attention weights to attend the important features in time. And the other one we call dynamic convolution, which aims to aggregate temporal information adaptively for each video. And these two operations are quite simple, and the combination of them can make a video recognition more efficient and effective. And our temporal module is a general, I think, network block. It could be easily incorporated into the ResNet block, and we can plug it in the bottleneck, and so the temporal computational costs are relatively small. And first, we do some ablation experiments to demonstrate its effectiveness. And for those baselines, we use the same number of frames. The first one, we just use 2D CNNs, and in the final layers, we use average pooling to aggregate temporal information. And its performance is only 70%. And then we perform some slow temporal fusion with temporal poolings, which means we use multiple poolings at different stage of the network. And we find this slow fusion strategy without any parameter tuning. And it can increase the performance to 73%. And we replace all pooling operations with temporal convolution. We observe that the performance gap is quite small. It's quite similar for temporal convolution to temporal pooling. And instead, we observe that if we use our temporal adaptive modules, we can easily achieve 75% or even 76%. And we also try different kinds of backbones. And our basic motivation is to use this module with 2D CNNs. So we try ShuffleNet, MobileNet inception, and we can also bring very big performance improvement. And after that, we also try some very powerful 3D backbones. We find even for 3D backbones, our temporal adaptive module can still improve its performance by 0.6%. And here is some comparison with SOTA methods on Kinetics 400. And we also visualize the temporal aggregation weights. We can see that our adaptive module can learn some adaptive weights according to the video content. For example, for some videos, the center frame maybe have higher weights, and while for some videos, the previous or the next frames have higher weights. And the right is a weight visualization for I3D, and I think their weights are quite smooth among three, quite similar or quite smooth among 3 frames. And our second work we called temporal difference networks, and we observe that temporal information maybe may be shown some multi-scale structure, which means in short term we may capture some short-term motions. It also may be we need to consider some longer scale or long-term temporal structures. So we need to consider maybe a two-level motion modeling strategy. And our techniques is based on a new and efficient motion representation we call it temporal difference. And we aim to provide an alternative to frame stacking plus 3D CNN with an efficient module called temporal difference module. Here is an overview of our TDM. And basically, we think a video should be divided into several parts or several segments. And for each part, we need to capture the static appearance with a 2D CNN. And we also capture some short-term motions around each keyframe, I think. And this short TDM will compute the local motions, and it will supply the 2D CNN for better representation. And for the long-term modeling, we need to consider a longer range of temporal structures among different temporal segments. So we propose a long-term TDM. Here is some technical details, I think. For short-term TDM, we're basically using a residual connection to combine the motion information and appearance information. While for long-term TDM, we use difference-based temporal attention to enhance the segment level features, and they add back to the original features. And for more details, I think you can refer to our papers. And here is some ablations, and we do some comparative study to illustrate the effectiveness of difference operations. We can see that if we use a single difference operation for STDM or for non-TDM, it can improve the performance very largely, about 10%. And the right show the stage ablation studies. And here we also compare with some previous temporal modeling methods such as temporal convolution, TSM, and TNet. We can see our methods achieve the best performance while still with very low computational cost, I think. Here is some ablations for our methods on something data set. I think this is because for something data set, and they are should be motion-centric action classes, and so we need to better capture motion information for better action recognition. And for this data set and our methods achieves, I think, the best performance when it was published. And for kinetics data set, our methods with achieve very comparable performance under a very lower computational cost. And we also plot the flops with respect to the accuracy. We can see our methods can do a good trade-off between accuracy and computational complexity. And in the right, we reported the actual running time for our methods and some baselines. And in fact, our methods can only increase the running time a little bit, I think, and their performance is much better than some baselines. Okay, so I will introduce video MAE. In fact, previously we introduced some attention operations, and we all know recently the transformer is very successful attention modules for images. And I think in last years, several works are trying to adapt transformers to video domain. And the first one is called timesformers. and they do some different kinds of spatial temporal attention factorization, and they did some ablations. And from this table, we can see their difference are quite small, I think, and their performance is a little bit better than CNN. I think they got about 80%. Almost at the same time, I think Google also proposed VIVIT methods. Its idea are quite similar to previous papers. The only difference, I think, they investigate different tokenizers. So we observe that when we adapting transformers for video understanding, they face two difficulties. First, they need very large scale pre-training, and they also heavily depends on pre-trained models. In fact, for video, I think the temporal redundancy and coordination make the pre-training even more important. So we ask a natural question, whether we can efficiently train VIT purely based on videos without using any pre-trained model. And at the same time, I think Kaimin proposed a very efficient method called MAE. So our video MAE is a natural, I think, extension over MAE, and we try to solve in two aspects. First, we will try to perform self-supervised pre-training with mask autoencoder, and we propose a new masking strategy, I think, called tuple masking with a high ratio. And I think we first propose a very simple mask autoencoder. We just using the reconstruction proximity task, which is similar to image MAE. And as the symmetry, I think the architecture in MAE, so our pre-training is quite very efficient. And the second, we observe that there are some unique characteristics with video data, and we observe that video may have quite high redundancy. As shown in this example, we can see the frames are quite similar. So we propose a new masking called tuple masking. It's in the last, I think, in the last row. And in this case, we can avoid information linkage, I think. If we just random mask patches, in fact, we can find some patches will appear in different frames. So we can easily reconstruct the missing patches. And so we use tuple masking, and we also find the redundancy. We have to use very high masking ratio to making the video reconstruction as a more challenging task. And here is some key evaluations. We perform experiments on something dataset. The first is about masking strategy. We think our tuple masking is more effective than a random masking and a frame masking. And we also compare our video pre-training with some image net-based pre-training. And we think we can see our video pre-training is much effective than image net pre-training. And finally, we also compare with the dataset size. We think the dataset size is not the key. In fact, the data quality might be more important. Here is some evaluations on the masking ratio. We can see 90% or even 95% masking ratio is quite good for video MAE. And here we compare MAE-based pre-training with training from scratch or with contrastive-based pre-training. We can see our video MAE is more effective than the other two training methods. And in the table 4, we compare its training time, and we can bring about 3 times efficiency, I think. And in the left figure, we can see that our video MAE can work very well for small scale video dataset. In particular, for HMDB, we only have 3,000 videos, and with video MAE pre-training, we can obtain 60%. I think this is quite better than previous sorter methods. And here is some sorter comparison. And first on something data set and our video MAE, without using any external data, we can achieve 75% performance. I think this is the best performance of this data set so far. And we also compare on kinetics data set. I think without any external data, we can achieve about 85%. I think it's also a quite strong performance. And we also transfer the video MAE performance to action detection. And we think its performance is also very good. So here we give some visualizations. We can see for some cases, it can still achieve some satisfying reconstructed examples. Okay, so the summary, I think for video MAE, we present the first, I think, video mask autoencoder. And it is a simple and data efficient and strong methods. And it can achieve leading performance without using any extra data. I think last, maybe I quick introduce our multi-sports benchmark. And as we can see previously, some methods will only focus on action recognition. However, if we look at their categories, are quite cost-efficient, I think. And also they require no localization understanding. And even for action detection, the existing benchmarks are quite small. And even for error, I think they are quite primitive atomic actions and no temporal localizations. So we think we need to introduce a new benchmarks for more complex and more challenging action understanding. And we think for real world applications, maybe localized and detailed understanding actions is quite important. For localized, we need to focus on multi-actor scenario, and we need to we call this is big view video, because in this video we may have multiple actors and different actors have overlaps, have occlusion, I think. And for understanding, we think we need to focus on more fine-grained classification, because the existing benchmarks are relatively cost-efficient, not fine-grained. So we propose our sports benchmarks. And the first track, we perform multiple object tracking. Here is a small video, and this is for volleyball. We perform actors tracking. And I think for time, maybe we can. And the second task, we focus on some key action classes. In fact, our benchmark involve four sports events. The first is gym, and the second is basketball. And we label some key actions. The third one is football. I think for time, I will skip the demos. And here is our some statistics. I think it's quite a challenge, and the long-tail distribution and some statistics. And here is some baseline performance, and their numbers are quite smaller than previous sort of data sets. And currently, we also try to label some higher level interactions between multiple actors. For example, we are labeling some serve and first pass and second pass. And attack and defend. Okay, so here is an advertisement. If you are want to doing some challenge, please you can check our website. So here is a conclusion, and I think in this talk I first introduce some efficient video models, and we try to address the computational efficiency. And as the second, we propose video MAE, and we try to address the data efficiency. I think in the later research of action and understanding, we should shift from simple classification to deeper understanding. There may be multiple aspects. The first one may be the non-form video understanding, just like this workshop focus. And we can also focus on some big view understanding, and because it involves some complex interactions. And I think we also should focus on some fine-grained video understanding, because for some real applications, I think their actions understanding requirement are many also about fine-grained action understanding. So here is my summary. Okay, so thank you.
Yes, thank you, Li-Ming, for the wonderful talk. Let me see in the chat channel. There seems, if you have question, from online attendance, if you have question, you can type in the chat channel. I'm not sure from the conference, the new audience, if there are any questions. Okay, maybe I just ask a quick question. I'm very interested in the video MAE work. And
yeah, he's giving you the.
Do you know, like, I'm curious about how do you construct the tube, like using some tracking, object detection methods, or some kind of like, I don't know, could you elaborate more on that?
Yeah, I think, yeah, in currently we assume, I think the motion are quite small, are not so fast. So we're just using a strict tube to mask the whole video. In fact, if we can make some motion estimation, I think we can focus on the foreground, and maybe we can focus on the activity itself. And if we have those information, we can make the masking more effective, I think, and making the mask and reconstruction more effective. It may be can encourage to learn more effective representations, I think.
I think, yeah, I think that's brilliant. This kind of straight tube is very efficient to compute. Yeah, cool. Yes, thank you, Li-Ming, for the talk. I think Bernard is there already.
Yeah, thank you.
Yes, thank you. Maybe Katia, you can help introduce Bernard.
Yes, actually you can. Sure. Hi, everyone. So I am Karthik, and it's my pleasure to introduce Dr. Bernard Ganem. Dr. Bernard Ganem is Associate Professor of Electrical Engineering and Computer Engineering and a Deputy Director of the AI Initiative at COST. His research interests lie on computer vision and machine learning for advancing in the realm of artificial intelligence applied to surveillance, autonomous vehicles, smart traffic control. Dr. Ganem is also the father of cutting-edge avatars for environmental and archaeological investigation. So without further ado, here is Dr. Ganem.
Thank you. All right, so let's see if this works. I want to thank, first of all, the organizers. Holding, from my own experience, holding a hybrid conference is way harder than holding a in-person conference or a virtual conference only. So bear with us. All right. So my talk today is about, so I'm sorry for wearing a t-shirt that contradicts with this workshop. I came from there. I came from the ActivityNet workshop that's being held at the same time. What I want to talk about today is what we've learned over 7 years of ActivityNet. I'm sure a lot of you have heard about it if you work on temporal activity localization or various tasks that are included in the ActivityNet workshop, you know about it. We've been holding it for 7 years now. This is the 7th year coming. So after 7 years, it makes sense to look back and see where is the field going, what kind of progress have we done, and what remaining challenges are there. All right, thank you for the whole team, obviously for my team that have made this possible, especially Fabian Kaba, who is actually the real driver behind the ActivityNet workshops. So ActivityNet, for those of you who don't know, is a data set that we published in 2015. At that time, it was the largest temporal activity localization data set out there. It was focused on localization, not classification anymore. You're not classifying snippets anymore, but localizing activities in a longer video, which is the theme of really this workshop. At that time, it was the largest. It had 200 classes. The activity classes that we had spanned the spectrum of daily life. Natural actors from YouTube, because of user-generated video from YouTube, and there was a hierarchy that came with it. So it was a great feat. It took us a long time to annotate and put it out there. And since then, we've been holding a workshop on it. So not only are we now in the workshop showing ActivityNet tasks, but there's tasks that have to do with other data sets and many other interesting tasks. Including there's another data set for TAL called HACS, SoccerNet, AVA kinetics, active speaker detection, so forth and so on. So what specifically I'm going to talk about today is TAL, or TAD, some people call it TAD, which is temporal action localization or detection. Meaning you want to find something small of interest inside a longer video. Okay, so let's say you're interested in pole vault. Here you have what you're trying to find is a class that has examples that you've seen in training, and then there's K of these classes. Of course, you could generalize this idea of localization to language-based localization, meaning I give you a description in language of what I want, and I want to find. That's usually called video language grounding. But localization is localization. Either it's from a discrete set of classes or from language. So let's just focus on the former, which is TAL. So you have a K number of classes, and you want to find the beginning and ending of every instance of that class in every video. And usually you have long form, right? So these videos are pretty long, and what you're trying to find are shorter. So here is a trend over the last 7 years of ActivityNet challenge in terms of the average mean AP, which is our metric, the mean AP over multiple. Okay, did I step on something?
Should be back. There we go.
All right. So this is the trend over the years. This year, the winner got 45.85 average mean AP, an improvement over last year. There's always an improvement. That's good to see. But you see that there's stagnation. And just like any other data set, things happen and things stagnate. And although there's been lots of progress in terms of methodology over the years, we'd like to go in and do a deep dive of why is it that we're stagnating? Averaging an improvement of 1-2% per year is not bad, actually, because this is average mean AP over multiple temporal IOU thresholds, right? So it's pretty significant. But why aren't we doing much better? To understand that more, let me just describe for you a typical TAL approach. This is typical. And for those of you who are new to the localization realm, you might be surprised. But this is what we deal with on a daily basis. If you look at localization, usually you have a video encoder, like what Liming talked about before. Pick your favorite one, whatever it is, pre-trained on your favorite data set, and you freeze it. That's the main problem. So this goes back to when I was a grad student, where we were picking up features from left and right, dense trajectories for all of those who know what dense trajectories are, or IDT, the improved dense trajectories from Cordelia's lab, if you use that, or a whole bunch of other features, and then you build a detector on top of it. So it's not very different from before. Now you have some deep learning-based feature extractor, and you freeze it. This we'll see, is the main problem that we should try as a community to fix. This is absurd that we live in a deep learning era where we still do this for video. We need to find out. It's a big problem. It's very hard to solve. I'll talk about it later, but it's one of those great challenges that we need as a community to resolve. This is not the way to go. But anyway, these are typical TAL approaches. You have a frozen video encoder that's usually pre-trained on a classification task. So kinetics, for example, 700 is a popular one. You could pre-train it on whatever you want. Usually it's kinetics. Then a lot of effort has been done on full fidelity TAL, which is you focus in on the localization method, the detector basically. So here, for example, you do not backprop through the encoder at all. So this is the typical way to do it. Okay, so having said that, one lesson that we learned is that it has something to do with whether these methods that we're training are actually using context, temporal context, to detect where particular activities are in the video, because that's what we want. I mean, ideally, you you look at what's around the activity instance to understand where it begins and ends, right? That's typical. That's what humans do. And so we ran some human subject studies earlier to understand whether this is possible by humans. You show them a video, you show a human observer the video, you show them up until a certain context size before or after the activity instance, and ask them, will there be an activity happening? When will it happen in the future or in the past? And they will tell you. They will give a good guess. And this is kind of the results that you get. So these are percentages. So 32% of the ground truth of the activity net, they can be detected by a human observer at 6 context size units, call it, but it's as a unit, away from the actual ground truth activity. This 0 means that it's very difficult to predict what's going to happen. These are usually videos that are generated by pasting multiple clips next to each other that are pretty much not necessarily random. They're semantically related, but they're different clips altogether. So this is where there's 13% that are 0. But there's a lot that you can actually use context. Humans use context to localize. Now, let's see what the winner of this year looked like on those ground truth categories of context size. So over here on the x-axis, you see these are, we categorize all the ground truth activity instances that fall into those context size categories. That means the ground truth activities here in the 6th bin are the ones that humans can actually localize 6 context size units away from the actual activity. And what you see in the bar plot at the y-axis is the mean AP, the average mean AP for this method, the winner of this year, the best ever, on each of these categories. What do you see? Inversely proportional or monotonically decreasing performance across the context size. And this is not only, I don't want to blame this method or another method. This is the same plot. I regurgitate the same plot over and over for every year. This is the same plot for all the methods. The reason why, what does this mean? That means that we're doing very badly on the ground truth samples where context actually makes a lot of difference. And we're doing very well when there's no need for context. This is what it means. What does this tell us? Well, something's wrong, right? I mean, we should do a better job at making use of context. Another lesson learned that we have is that, there's a paper that we had published a few years ago called DTAD, where you generate a report on how good or bad your TAL method is. Okay, and if you ever participated in the ActivityNet workshop, you get an automated DTAD report given to you after you submit your competition file. Okay, and this is it doesn't just give you an average mean AP scalar number. It tells you where the false negatives, where the false positives, what kind of errors you're creating, and by far the biggest source of error in all the methods that we've seen up until now is localization error. So we're pretty good at classifying what the activity is, but finding the boundaries, tight boundaries, is not that good. So that's an issue, and it still remains an issue. And in my opinion, this issue comes from the fact that you're freezing a video encoder that was pre-trained on classification, not for a localization task. You have to keep that in mind. What's good for classification doesn't mean that it's good for localization. So imagine, what is the analogy of that in images? So imagine you want to build an object detector on Coco, but you froze the backbone architecture was pre-trained on ImageNet, you freeze it totally. And then you want to try to build a detector on top of those frozen features to be. So obviously, people do fine-tuning. They fine-tune these backbones on the data sets. This is not possible here. And I'm guessing the reason why we have so many localization errors is because of this particular problem. The features themselves are not good enough to discriminate between across the boundaries. So this is going to be some shameless advertisement of my group and what we've done over the years in TAL, but I think it gives some good insights on what we've done and where we can do more. So one thing that goes to the point of exploiting temporal context is the idea of how do we do how do we encode long-term temporal context? What we've done over the years, we've shown that using graph neural networks can help with that, right? And the transformers, for those of you who think that they're different, they're not really. So there's going to be a graph neural network tutorial tomorrow. I'm giving a talk there, and I'll be re-emphasizing this point. So graph neural network on a graph that is complete, that means everything is connected to everything, okay? And using, for example, a particular aggregation function. This is what in the graph domain we call it aggregation function. If that is attention-based, operationally, that's exactly a transformer layer, right? So there's no real difference. But with GNNs, you can do a bit more. And it's pretty versatile, and it's pretty generalizable to many other cases, many other applications. So anyway, so we've had made innovations on the GCN side of things, generic toolage that can allow us to go really deep in detecting, segmenting graphs, general graphs. So we thought, why not we apply it to video? And this is what we got. We call it GTAD. This was in 2020. It's still a good method. So usually what happens is that you have this clip encoder that you pass through the whole video, and then you have these video groups, and then you try to apply a detector on top of it with these particular features. So really, the clip over here rarely interacts with the clip farther into the future, which is where the context helps. So instead of doing that, imagine each of these video clips that you segment out of sample out of the video is a node in the graph, and you connect them in some way or another, and then you train a GNN on top of it that's deep enough. That's what GTAD is all about. That's what I was trying to do. Now, the type of the connectivity that we had was two types. You have temporal connectivity. So if you're a graph node, temporally consecutive or a predecessor to another node, you're connected. And you have another type of connectivity, which is called the semantic connectivity or dynamic connectivity based on your features, your actual features, not in terms of time. So in essence, a video, this is the time domain access. You can start it off with a red node over here, and it propagates it through time. These are the nodes, and they're connected consecutively because of time, and they're also connected across, right? So these longer term connections, what we can see as context, meaning that knowing about this will help you know about this. You see that there's connectivity between, even outside the actions. The action goes from here to here, right? And then there's a stop, and there's another action over here. So you see that there's also connectivity across actions, which is actually quite interesting. So not to bore you with the details, but there's a GCN, a graph convolutional network, with the flavor of a ResNext. So we call it GCN Next. If you people like coining new terms, and so that's a GCN Next. It's a kind of a module that allows these graph nodes, these video clips, to interact to create a richer representation. And in the same way that there's ROI align, in faster SNN, there's an SG or subgraph align to be able to detect instances in a video. Because once you have a graph, what is an activity inside a video? Well, it's a subgraph inside this bigger graph. So you're doing subgraph detection inside a graph, and therefore, how about you use a SG align instead of an ROI align? So it basically it runs similar to a faster SNN kind of setup. It's proposal based, and that's a two-stage approach. And you do, your regular regression at the end, and you get some good results and improvement at that year. But what's interesting is the following. So to show that actually it's using context, let's take two videos. So here's a video of, I think this is arm wrestling, I guess. And so it's represented in this graph format where you have these green nodes are the video clips contained inside the actual activity, and this is background, the yellow is background. Here's another video with, again, something similar. You see there's a connectivity between, this is learned connectivity between this node over here and in the background, meaning something in the background, video clip in the background is actually propagating information into a video clip in the foreground, in the activity, to represent it better. This was kind of the best linkage that was trained from the GNN. Same thing goes for this video. Now, what would happen if you took the background from this video, you splice it with the foreground of this video, right? That's something that one can do. You can splice up a new video, and now you have a new Frankenstein video where you have the foreground from this guy over here and the background from this gal over here. Okay, what do you see now? There's no connectivity between the background and the foreground. Why? Because probably the background of this activity over here is totally irrelevant to the actual action that you're trying to detect. And so in these cases, context was shown to be useful, and over here not. And this GTAD is actually learning these connections automatically. You don't need to actually connect them for yourself. All right. So on the second point of classification is easy, but we have to define better activity boundaries. We need to work on the video encoder itself, and we've done quite a bit of work on that. Not necessarily the architecture, but how you train it. So we have XDC, which was our attempt to do self-supervised learning to train video encoders. And that was the first time that we showed on classification tasks that you actually can outperform fully supervised pre-training on kinetics. Then we have BSP, which is the kind of semi-supervised way of pre-training. And actually this won the Track 2 challenge last year in this workshop. And then there's a fully supervised pre-training method called TSP, which is very helpful in improving performance, but it's fully supervised. So you have to use the same data set that you train on. So just very quickly, I don't have much time because there's a lot to cover. XDC is all about self-supervised learning using audio and video together. We tried using contrastive learning. It was difficult at scale to use at that point, at that time. So we ended up using something simpler, or supposedly simpler, called deep clustering. And the idea of that is that you have some video frames over here. They will generate for you labels automatically. All of this is unlabeled data, by the way. You will cluster the video features to generate labels for the audio signal and vice versa. So the idea is that if two videos sound similar, they should look similar. And if they look similar, they should sound similar. That's kind of the overall idea. It's not necessarily correct in every single case, but that's the overall idea. So by coming up with this multimodal deep clustering problem and training it on Instagram 65 million, you get amazing results. And this is what you get. So you outperform other self-supervised learning methods. Great. But what's interesting is that as you increase the size from kinetic size, several 100,000 to 65 million videos, this is, by the way, work with FAIR, you get actually, for the first time, you get improvement over fully supervised pre-training using kinetics. And this was, to our knowledge, the first time that this was shown to be possible. And what would happen if you added it as a backbone to ActivityNet? You can actually get a bump of 0.5%, 0.6%. That means you take your pre-trained, fully supervised pre-trained backbone that you were trained on, let's say kinetics. If you replace it with the XDC version, the SSL version, you get a 0.5, 0.6% bump without doing much, right? It's just ripping out the backbone and replacing it with something else, okay? So that's great, but let's rethink how we do pre-training in general. In the image world, we pre-train with ImageNet, let's say, and then we fine-tune on the downstream task. We pre-train on kinetics, but we tend not to fine-tune. We can't fine-tune because of memory issues and a whole bunch of other problems. We cannot fine-tune on localization tasks, unfortunately. So we need to find some intermediate ideas to get us towards that. Ideally, the holy grail is end-to-end learning on localization tests and video. Okay, that's going to be one of my take-home messages. Whoever can solve that is the holy grail. I mean, you will become famous, but if you do it properly. And without maybe subsampling significantly in time and space, of course you can do that, but on not necessarily the original resolution, but on something reasonable, can you do end-to-end training for localization tests and video? That currently is not possible. But so what kind of tasks can you come up with that are intermediary that could help with this? Let's show that actually this is a problem. So remember, I told you that localization is a major source of errors for all the competitors in ActivityNet. Let's show qualitatively why that is true. If you took all the video features of clips in a particular video and you align them in time, so this is time over here, each one of these are clips, and then each of these are clips, and you do a cosine similarity between their features. Pre-extracted frozen, right? The green interval over here tells you where the actual activity is. So for example, if you had frozen your features and you got something like this, there's no way for you to determine when from the basic features that are frozen, you never fine tune them, to know, it's going to be very difficult for you to determine when the thing starts, when the thing ends, given this kind of cosine similarity. Okay, I think we're all in agreement on that. What about over here? Well, here you have lots of video clips that are very similar to each other and then very different from each other within the same activity. And over here is just, sometimes similar, sometimes not. And over here, it's similar into the background, which means that it bleeds into the context. So this is the reason why localization is a major source of error, because we freeze the features, and this is how the features are correlated across boundaries. So BSP was our first shot at solving that in a weakly supervised way. As I said, it won the track 2 part of the challenge here at LoveU. And the whole idea is that, can we generate an augmented video data set, a synthetic one, where we know where the boundaries are? Okay, can we create boundaries? The answer is yes. What you could do is you can take 2 action classes or videos of action classes from kinetics and splice them together. What you could do is also, run, that's a different class, one of the types, the different class. The same class, you can have them in, different instances of the same class, you can put them together. Since you're synthesizing this longer video, you know where the boundaries are. So you can help augment your localization task. Different speeds also helps, meaning that you can run one video on one side faster than the other. And again, you can create this Frankenstein video where you know exactly where the boundary is. And you can create as many boundaries as you want and as many videos as you want. Turns out that if you train it on that kind of data, okay, and so this is how it looks like. You basically take one video class and a video clip and you bleed it into the other and then create a fake video, basically, with a boundary that you know. So if you have an encoder now, your usual encoder that you use, the backbone that you use, it's usually trained on classifying particular class labels for the clip. But if you could also build this BSP encoder that tells you whether this clip is one of the 3 classes of synthetic creations that we created. If you can train it on that Frankenstein data set, turns out that this vanilla encoder that you have over here and this BSP encoder gives you a representation that's pretty good for the downstream task of tau. So this idea of allowing the encoder to not only know whether the video clip that it's looking at is a particular class or not, whether and enforcing that it be sensitive to boundaries, meaning does it know the difference between a boundary between 2 of the same class or 2 of different classes or a change in speed, right? If you supervise it to know more about how boundaries look like, you get a better encoder that allows you to do better tau. That's the idea, and this is what we showed, improvement of 0.5% and on top of GTAD. So BSP can be applied to anything, right? BSP is a video encoder pre-training method. So you can apply it to any detector you want. We use GTAD because we created GTAD. You can use it for any, it's not only for tau, they could use for crosstasks, another localization data set, charades STA, which is a video language grounding task, which is where you're not doing tau anymore, you're doing language grounding, and you see the improvements just by doing this artificial synthesis of videos. Okay, so going back to this, this is what we had before with frozen features that we didn't use boundary sensitive pre-training. And there should be a result here. Okay, it's over here. Sorry. Yeah, let me just figure something out. So that was BSP in a semi-supervised way of pre-training. TSP is something very similar, but it's fully supervised. So let's say you have a localization data set. You know where all the activities are and what their labels are. Instead of training your video clip encoder to classify whether that clip is one of the K classes, just add another supervision to it saying that, okay, is this video clip class 1, 2, 3, or 4? And is it inside an activity or outside? That's it. That extra localization binary output is important because it tells you whether whether you're inside an actual activity or outside. And this requires you to have the localization data set available for you. If you do that, you get major improvements. Okay, so for all of you who are working on ActivityNet, this is a free pre-training technique with any encoder that you want. Doing this fully supervised pre-training will give you a performance bump if you're chasing after SOTA performances. Okay, so this is basically free of charge. Okay, so pre-training is very important, and this is what we had before, meaning everything was jumbled up because your pre-trained frozen video encoder is not aware of boundaries or the localization task. This is what happens on these same videos if you use TSP-based pre-training. So you see here now it's much easier to segment out or localize where the activity begins and ends. Same thing over here, same thing over here, same thing over here, right? So it actually improved. Why? Well, we got an indication of this from the average mean AP, it improved, but here qualitatively, it shows you why that's improving. All right, remaining challenges. And this is the last couple of minutes. I know I'm just at time, but it's good for you to know what the remaining challenges are because it could be the future topic that you work on for next CVPR or into the future. It's something that the community needs to work on, in my opinion. And these are not going to be strange to you. I'm pretty sure you all know this, but I just want to nail down the importance of these challenges. Number one, or I don't want to order them. It's not number one, number two. This is just two challenges that are very important, equally important. Okay. Long form, talking about long videos, short actions. Okay, this is aligned with the workshop and aligned with ActivityNet and so forth. You have, and this is the distribution of the ground truth instances in ActivityNet. You have many more extra small activities than you do large and extra large. So this stagnating performance increase is related to that. So we're getting better and better at these three categories of activity instances, but we pretty much are not getting these small and extra small, which is kind of how nature looks like. Like naturally, you have small activities within longer videos. So this is the mean AP with respect to each of these categories. Look at that. Again, you have high mean AP for the extra large and large, and it just dwindles off for the smaller ones. There's an issue. This is the same thing. This is akin to detecting tiny objects and images. How do you detect an object of 10 by 10 pixels? Same thing. How do you detect a few second activity inside a longer video? We need to come up with solutions. One solution, I'm not going to go through too much of it, is like using multiple scales for video feature representation. So instead of having one scale for the whole video, I have multiple scales. Some scales are good for the extra large and large. Other scales are good for the small and extra small. That kind of idea. This was published last year in SCP. It's not the end-all solution. This is just a challenge that's out there, and it's a really serious problem. So those plots that you saw about how the average mean AP exists in each of the categories of length of activities, that comes from the DTAD report. This is why DTAD is, I think, so important. It gives you where your errors are and what you're doing better at in the various categories, right? It shows you obviously whether you're doing better in the small or extra small, if that's your target. Okay, so please, make use of it when you're working on such a problem. So the BSP and TSP pre-training techniques that we have, they're just a way to is a cop-out for us not being able to solve the holy grail problem of end-to-end training for localization. Okay, so similar to what people do in the image domain, if you want to detect objects in COCO, you take a pre-trained network, an ImageNet usually, and you fine-tune it on your data set. Can we get an equivalent to that here? There have been attempts, I have to say, from my lab and other labs where we try to leverage kind of downsampling in time and space aggressively to be able to fit into the GPU and so forth. But I feel that that's not really the major solution here. There has to be other solutions. The reason why we can't do end-to-end localization training, either for video language grounding or for TAL or for any localization method application, it's because of memory issues. You cannot load this stuff into GPU. That's the main problem, right? Even if GPU, you have an A100 that has 80 gigabytes, and we do, still that's good for only a few videos in your batch. So we have to think collectively of ways to do this. So a way to approximate that a bit and not to solve the problem really, is to do it in a two-stage approach. This was from NeurIPS last year. We call it low fidelity TAL. So the idea is, okay, you start out with a video encoder that you pre-train on a classification data set, as usual. You take that encoder, but look what you do here. You downsample aggressively your video spatially and temporally, the localization data set, right? You downsample it significantly. Okay, over here, you see that now this purple line is what is the backpropagation kind of line. It backpropagates through the encoder. But on which videos? These very aggressively downsampled, spatially and temporally downsampled videos from the localization data set. Whatever you can fit into the GPU. Downsample it to whatever spatial resolution or temporal resolution that fits. And then you do end-to-end TAL, right? With this encoder pre-trained from classification. And then, so you could do that in many different ways because you could downsample in many different ways, but you do end-to-end TAL on a very small, much smaller data set. Then what do? You freeze that encoder and you train a separate TAL method on that, right? So you do kind of an end-to-end fine-tuning of the encoder on the localization data set, but on a very downsampled version of it. And then you do this full fidelity TAL, which is what we're used to. That was our kind of surrogate way of solving it. It is not a solution to it, unfortunately. So we need to work harder on that. This is my last slide, take-home messages. I think I've talked your ear off in terms of end-to-end training. End-to-end training on localization, which includes TAL, video language grounding, whatever, all the applications which require you to find things or caption things inside a bigger thing, inside bigger videos. We don't have a good solution for that, and I'm open for collaboration on any of on this particular topic. It's a holy grail, really. Localizing short activities, which is in long form videos, is very important. There's still no good solution out there for it. Multimodality, making use of audio instead of just video, which is the usual case. People that work on ActivityNet or TAL, they kind of disregard audio or just use it as an extra modality. Maybe there's different ways of using audio. Maybe it's better. It could be leveraged to find boundaries specifically, because let's say your class is about playing the guitar. Once you don't stop hearing the guitar, even though you're moving your hands and the video looks similar, that's it. That's the end of playing the guitar, because the audio tells you when to stop. So maybe audio is a good modality to use for localization. It's not that well studied. And how do you go beyond activity classes to video language grounding, which I think is the next step. It's much harder to do. It requires you to understand language also. And there's also the grounding problem. On this front, we have a paper at this CVPR called MAD. It's a data set, large-scale video language grounding data set, where we took movies, many movies, and we can increase the data set however we want. And we use these audio narrations for that automatically are not automatic, that are manually created already for these feature films, and we localize them in video, so we can get a very large scale video language grounding data set that's not biased as opposed to the other data sets out there. So if you're interested in video language grounding, there's that MAD data set, MAD. It is very large scale. You can pre-train on it, very unbiased with respect to other VLG data sets. So I think if we're going to go to that stage of task, MAD could be a source of information for you. And with that, thank you so much. And I know I went over time. I do apologize. Thank you. We have time for questions or?
Yeah.
Yes.
Thanks a lot for the great talk, especially the pre-training part is pretty impressive. So I wonder, I have two questions. So first, do you think the pre-training, although the pre-training has based design or temporal foundation, I wonder if your team has tried to see if this kind of pre-training can even improve the video representation itself, right? Or generic action classification tasks. So that's the first question.
Yeah.
The second question is that for the pre-training, I wonder if you guys observe any possible failure cases, like if we imagine maybe for certain actions or for certain very complex actions, there might be some static frames in between two dynamic frames, right? For this kind of actions, will there be failure case during the pre-training is the appended non-action frames, actually similar to the frames in between the academic frames of action.
So let's start with the last part. So you're talking about BSP specifically when we just Frankenstein the videos, right?
Yeah.
Because TSP doesn't have that problem. TSP is using the TAL data set that you're given, right? And using that data set. BSP creates a new synthesized data set by splicing things together. I'm sure there's failure cases. I'm pretty sure there are. But from the overall performance increase, it means that it's definitely better than just freezing. So I think it's a low bar that we went beyond, and you're asking for a higher bar, and we should all strive for the higher bar. Yes, there definitely are failure cases. What was the first question again about the?
I just wonder if template is sensitive questioning how to see like classification.
That's a good question. We never really tried it. Yeah, we never really tried it. Maybe we could. Maybe we could try it. We never tried that. We thought of localization as we thought maybe we could see how well it works on TAL as well as other localization tasks like video language grounding, cross tasks, this kind of boundary detection. Love the LoveView data set. And so wherever there's localization, maybe we can help with that. And it showed that it is possible to help. We never went back and see if it actually improves on the kinetics one. That'll be something interesting to look into.
Excellent.
Thank you. Any other questions before we adjourn? All right. Thanks, everybody.
All right. Thank you, Bernard. And I think Cordelia is already in the Zoom. Maybe you can share your open your camera.
Sorry, Cordelia, for making you late.
Yeah, no problem.
Maybe you can test it out. And meanwhile, I do a very quick introduction of you. So Cordelia is a research director at INRIA and also holds a joint appointment with Google Research. She has been program chair for CVPR ETCV before and editor-in-chief for ITCV. She has been actively working on video understanding across many tasks like retrieval, navigation, recognition, QA. All of these often involve long video. So maybe without further ado, let's welcome Cordelia. Oh, by the way, the talk is 25 minutes and with 5 minutes QA at the end. So if you have any questions, if you are at the conference, you can go to this stage. Otherwise, if you're online, feel free to type in your question in the chat channel and we will adjust it at the end.
Yeah, thank you for the introduction. Can you see my screen, actually, my slides?
Yeah, we can see your slides. Perfect.
Okay, great. I'll leave my camera out and I hope everything is going to be fine because the internet today is really bad. We have a really big heat wave here in France and everything is kind of breaking down anyway. So let me start. So, and please do tell me if there's a problem. So basically the talk will be on large scale learning from multimodal videos. It's pretty clear that given the large amount of video data available, it's important to understand these videos. And maybe one thing to be reminded is that in the end, we really would like to have a complete story of a video. So it should include using different modalities, long range descriptors, memorizing what has been seen before, etc. So here, for example, as the head waiter takes him to the table, they pass by the piano and the woman looks at Sam. So we really want to describe what's going on. And as I've said before, what we really need is a multimodal video representation in order to precisely understand the video content. Requires to have access to all modalities simultaneously. For example, here, if you look at this video, we can see that the man is serving food to a woman, but only if we hear the question, is this Indian, do we know that the man is serving Indian food to the woman. Another reason to use multimodal video representations and data is that we can use the large-scale data for cross-modal supervision without relying on any manual annotation. And so the final goal would be to use the available data to perform not only pre-training, but also zero-shot prediction. I'll start with the video bird, introducing the video approach briefly, and then show two recent improvements, one for cross-modal supervision, and one how to learn from audiovisual modalities from image captions, and then conclude with then extensions to vision language navigation. The idea of VideoBird was to learn from multimodal videos. What we have here is the visual video and the speech transcribed with ASR. So here, for example, we can see, but in the meantime, you're just kind of moving around your skateboard. The BERT model learns the correspondence between video and speech and is able to learn from large-scale data. It takes as input the text as ASR and the video features, here 3D convolutional features, but more recently we're using vivid features as input. We can then use this model to train on a large-scale data set, here for example 300,000 cooking videos, and this which come with description. So here we can see on the left, keep rolling tight and squeeze out the air to its side. We can then use the learned model for zero-shot prediction. Here we have two examples of videos which we haven't seen before, and we can correctly predict the verb make and the noun pizza. If we could look at the results, we can see that the performance of our approach is on par with a supervised model, the table on the left, and the table on the right. And right shows that the impact of the pre-training data, the more pre-training data we have, the better the performance. So we can see here, this was one of the first models which learns video language correspondence. It's close to fully supervised accuracy on some tasks, and more data improves the performance. And here another example where we can show that by fine-tuning it for captioning, we also improve the performance, and this shows here that pre-training helps. So we've seen that this model works well. However, what it doesn't do, it cannot be extended to more difficult tasks and non-instructional videos. So the first approach which I'll introduce is how to get cross-modal supervision for another task, here for video question answering. So the approach just asks uses cross-modal supervision. To learn zero-shot video question answering, what's the goal? The goal is we have the question, what type of animal do we see? And the answer of our system is fish. We can predict this without having access to any supervised information. And to do so, we generate a large-scale video question answering dataset automatically. The idea is we start from the how-to 100 million dataset, which comes with ASR captions. We do use, that's why we say cross-modal supervision, textual question answering training. So we use a question answering trainers corpus, and on this corpus we train a transformer model. The transformer extracts questions and answers from the ASR caption. In more detail, on the left we can see what we have. We have a manually annotated text question answering text corpus, here squad V1, which comes with 100,000 question answer pairs for paragraphs from Wikipedia articles. This we can then learn to predict the answers first, and then given the text corpus and the answer, we can learn how to predict the question. The transformers are trained from this text corpus. What we do now, we have the how-to 1 million clips and the speech transcribed with ASR. This allows us to extract short clips with the sentence punctuation and using a recurrent network. And then we can predict for each of these short clips the corresponding answer with the answer extractor and the corresponding question. And so what we have now is we have for each of these clips, we have a question answer which we have obtained automatically. We take 1.2 million videos from how to 1 million. We obtain on average 43 video clips for each of the videos, which correspond each to a sentence. On average, a video clip is 12 seconds long and is associated with 1.2 question answer pairs. This gives out a total of 69 million triplets. We have manually evaluated the quality on a small data set. We can see that 30% of the examples are correct and matching, 39 are correct but the question answer doesn't correspond to the visual content, and 31 are incorrect. Here, an example of such a generated question answer pair. The ASR is add some of your favorite sprinkles, give it a mix. And the generated question is, what can you add to the mix? The generated answer is sprinkles. You can see here that this is correct. The video QA architecture is a video question transformer, which we train with masked language modeling, but then also with contrastive loss. And the contrastive loss is between the video question answer transformer, the video question transformer and the answer transformer. So we can actually learn using this contrastive loss from large scale data. Here we have 16 million different answers. And if you look at the results for zero-shot VQA, we don't use any annotated examples for training, and the results on state-of-the-art datasets are evaluated, but only used for testing. So here we can see the top row gives random performance. The row below, we can see that our results are very good. Of course, they're not perfect, but if you look at the top 10, we can see that the performance is satisfactory if you look at the top 10 replies. Here we show a result. So the question is, what is the largest object at the right of the man? Our answer is wheelbarrow. And if you use text only, we would predict statue. That's kind of the most obvious answer. But then if you have the visual information, we can actually predict the corresponding answer correctly. And then if we use our data for pre-training, we can see that using our how to VQA dataset for pre-training significantly improves the performance of using no data for pre-training. And we have seen that here we can use supervised learning to exploit the large amount of data available online. We rely on the correlation between multiple modalities, here video and language, where we use the annotations from a language corpus to transfer it to a video task. We show that we obtain excellent zero-shot performance. And one open question, obviously, is how to further improve the zero-shot performance and the correlation with the visual input. So ideally, we would like to filter the examples to keep only the ones where the question matches visual input. And then another problem which we have addressed is now how to improve the quality of our corpus. And here, this is another work where we actually want to exploit the fact that the correlations between images which come with which captions. So here we have image captioning data sets, such as conceptual captions, which comes with millions of annotations, is relatively clean. And then examine how to transfer those to videos to obtain additional training data. If we look at what we have for existing data sets, they are manually labeled in many cases, which is expensive and time consuming, and small, limited to certain domains. And then we have some semi-automatic or automatic data sets, for example, how to 1M, which is very noisy. We have seen before, only limited to instructions. Then there's web video text and Instagram hashtags, which have also some noise. And then in addition, they don't come with audio. And so here we have a data set where we actually start with images with captions. So these are data sets which are available. And then what we do is we use these image caption pairs to annotate video clips. And to do so, what we do is we match the image to the middle frame of the video clip. And if the two images match, we now have a somewhat reliable annotation of the video clip. And we can also use this as a correspondence between the audio and the annotations. And if we look at the distribution of our video CC 3 million dataset, we use the conceptual caption 3 million dataset as seeds. The size we obtain is 10 million clips. So you can have possible multiple captions per video clip and multiple captions per video. Our data set is multimodal. We have both video and audio. And if you look at the distribution, it's much more balanced than the How-To 100M dataset. So below, we show pie charts of the distribution of the different domains. We can see on the left the domains in video CC. You can see that many different categories such as food, hobby, vehicle, gardening, technology, animals, culture, many others are equally distributed. However, if we look at the domains in How-To 1 million, we can see that for the food category and then also the hobby category, they have the largest percentage. That's not surprising because How-To 1M is focused on instructional videos. If we look at a couple of examples, we can see here, person throws a pitch during a game against university. On the left, the seed image. On the right, the mined videos. You can see that they all correspond to the caption. Then another example where the audio is more relevant. Rap artists performing on stage during day at festival. Again, we find different clips where there are artists performing some concert. Another example is a sea anemone in a dark blue water of an aquarium. And then finally, this is a statue. And here what we find is mainly video clips, which are static clips, so they don't contain any motion. And that's something which we're actually currently working on, is to filter out the clips without motion because they have no information on training a video-based model. If we look at the failure cases, we can see here, we did a study of 100 samples. 91 are relevant, 9 are not relevant, 31 are somewhat relevant, and 60 are highly relevant. And if you look at the left, you can see we have the robot playing an electric guitar. The first correct clips are correct, but then the last one, the robot is actually holding a device. Second example, cricket players embrace cricket players. We can see that the two first ones are correct, but then the last one, it's not relevant. And then maybe most interestingly is the last example, the view of a red car blurred through broken glass. We can see here the first example. Actually, interestingly, it finds the exactly matching clip. So I guess it has found the correspondence perfectly. And then if you look at the two other examples, we can see that we have broken glass, but no red car. And this is kind of very easy to explain. If you look at the visual similarity, what's dominant in the image on the left is the broken glass. And so basically what the features, the global features, what they match is the correspondence between this global image content. But then basically what's important here is the red car, which is not there. So here, this gives an idea how to further improve this data is by having some more precise matching between the objects in the captions and the content in the video. We can now use this data set for zero-shot video retrieval. So video retrieval is a task where we have a caption, a text query, and we want to retrieve the corresponding video correctly. On the first row, we train our model with How-To 1 million. We get a recall at 1 of 8.6. If we now use video CC 3 million, which has significantly less data, we can actually see that the performance improves by 10%. So basically, it gets more than twice as high. And this shows that basically for training these models, it's very important. The quality of the data is very important. If we now add audio, we can see that our performance further improves. And on the table below, we compare to the state of the art. We can see that the model improves overall the state of the art approaches. We can then also use this data to train a model for video captioning. Here, we're one of the first to show zero-shot results for video captioning. So the idea is we train a decoder-encoder model on this video CC data. And if you look at the table on the right, we can see that our approach significantly outperforms a model which was trained on how to 1 million. Of course, there's still a gap between this model and the fully supervised model. But then if we look at the examples below, we can see ground truth. A man is discussing the parts in an engine compartment in the vehicle. How to 1 million. So I'm going to go ahead and remove this, which is not very correct. While video CC 3 million, model trained on video CC 3 million says you get the engine bay of an automobile model. And then similarly, if you look at the two other examples, ground truth, clouds are moving in the sky. How to 1 million trained model predicts it's a great place to live and it's a great place to work, which is not really at all appropriate. And then our model actually completely correctly predicts clouds moving in the sky, in the blue sky. So it's actually more precise than the ground truth, which is one of the problems when you evaluate video captioning. And then last example, this is about sport players making big plays during the game. Again, we can see that the model trained on how to 1 million. It's not very precise. Then our model is actually more precise maybe than what the ground truth annotation gives. We can also use our data set to train a model for audio retrieval. And so here, what we have, can see that if you compare the state of the art of our model, pre-trained on how to 1 million, you improve the state of the art. And then if you use video CC, you get a further boost in performance. And then again, most importantly, you can see if we use this data to train a zero-shot model. So here, what we have is we have queries, and we want to retrieve the corresponding audio. On the audio caps data set, we can see that our model improves significantly over a model trained on how to 1 million. Again, obviously, you can see here that the gap with a fully supervised trained model is significant. But then basically here also one problem is that the audio in many cases doesn't correspond to the captions, and this is something which we could also improve over by further cleaning of the data set. We have seen that we obtain excellent results for zero-shot audiovisual video retrieval and zero-shot video captioning. It also shows very clearly the importance of the data used for training. And then open issues are further cleaning, how to make the data, improve the data further, how to extend the data set, and how to refine the temporal alignment. And in the last part of my talk, I'll show how these models can be also applied for vision language navigation. And in this case, the problems are very similar to what we have seen previously for video question answering and video retrieval. The task of vision language navigation is to train autonomous agents to follow natural language instructions to navigate in indoor environments. So these are semi-artificial indoor environments which are created from scans. And what we have as an instruction, it's not the full path, but just one instruction: go to the bathroom in the bedroom with orange stripe, make sure the faucet is not leaking. It's really one high-level goal which is given as input, and then the agent has to navigate to a corresponding location and localize the object. And so here, what we do is we design a fully transformer-based model. If we look at the model, what it takes as input, obviously the language, which goes into a language transformer. Then what we do to keep the information which we have seen before, have a hierarchical vision transformer. And here it's very similar what we use for video. What we model is we model individual locations and then how these locations visited evolve over time. So this can be seen actually as a video, where basically the video here is the assembly of locations in the video. And then last, we also input the current observation. Each observation comes with multiple views. That's kind of by construction of the data set. And then we use a cross-modal transformer encoder to predict the action. And so very similarly, what is used For video encoding, we use here bit for single video image encoding. Then we have a layer for encode the parameter views for multiple view encoding. And then on top, we have a general transformer for sequence encoding. This is very similar what we use, for example, in Vivid for the video representation. The only difference here is that we have an intermediate step where we also represent the correlation between the different views. And then very similar again to what we saw before. We do end-to-end training with several losses. We use common vision language tasks as proxy losses. So one is masked language modeling, masked region modeling, and instruction trajectory matching. And then here we use two new proxy tasks for vision language navigation, a single step action recognition, and a prediction of the spatial relations. And then if we look at what's important, how important is the history encoding? So many of the state-of-the-art methods, they use a recurrent network, a fixed size network to encode the whole history. This is the results on the left. We give success rate and the path length, success path length. And then the next is if we use only one view per viewpoint. So if you use only temporal information, we can see that this improves the performance. And then if you use a hierarchical encoding of the parameters, we will improve the performance. And next, how much does the visual representation help? Compare here different representations. The first is ResNet, pre-trained on ImageNet, VIT, pre-trained on ImageNet, and then VIT end-to-end optimized on the VLAN task. We can see that basically, similarly, what we have to observe for video representations, we do get a boost in performance by using an end-to-end trained VIT model. And then another question, how important are the proposed proxy tasks? So we can see that by using the vision language proxy tasks, we get already good performance. Then by adding the single step action prediction and the spatial relation prediction, we get a further improvement. So again, here we see that the vision language pre-training is important. If we compare our method to the state-of-the-art, we can see that it outperforms state-of-the-art on a number of existing data sets. And the approach was the winner of the Reverie and Sun Challenge, Soon Challenge, in conjunction with SCV 21. And so what we see here, that transformers can also be used to predict actions. Standard vision language losses improve the performance. Additional pre-training data is useful. And open questions are how to improve the generalization to unseen environments. What we do here is we memorize paths given on seen environment. And so the question is, how can we further improve generalization to unseen environments? And then do this, one idea which we're currently exploring is how to collect additional training data and how to improve the models. And then one other interesting question is how to apply this to real robots. Okay, thank you for your attention. If you have any questions.
Yes, thank you, Cordelia. I think there is no question from the chat channel. Maybe Wei Yao, is there any question maybe from the venue, new audience?
Right now, we don't see any questions from the audience. Is there a question from
Okay, maybe I just ask a very quick question. Thank you, Cordelia, and it seems a very interesting work. And I wonder for the last part of navigation, if we can somehow utilize your to synthesize the QA data set, the pre-training data set to leverage that for improving navigation, would that be possible?
Yeah, I think that's a very good question, but I think there's too much of a domain gap, right? So basically for video question answering, it's tailored to the question answering scenario. So basically A, the language doesn't correspond to the navigation, and B, the videos are also different. So I guess what we showed is that we can use more data for pre-training, and it kind of improves the performance, but then the model is quite different, right? So we have these multiple views, it's discrete, it's not continuous, right? So basically in the VLN scenario, we have discrete steps. So it's not like a continuous video, but it's a similar approach, but the steps are discrete. And so I think you cannot transfer it for this number of reasons, but what we have looked at, we've looked at two things. One is collecting internet images from houses. This is another, it's AirBird. So it's a data set where we collect additional data by searching for house images. And then once we have these house images, we can use those to, like, similar to the other work on video question answering, but here with a different data set to get additional environments, right? This is the first thing, and we can show by having this additional data, we can improve the performance. And then another thing I think which is interesting, that's actually a paper at CVPR, how we can build maps on the fly. So this is actually Duet, which is another approach which we have developed, which can actually build these approaches on the fly. And then we can actually memorize what we have seen before. And this allows us to get rid of somehow of this generalization problem, because we can really use this newly built map to better navigate. And then the last thing we're currently looking is how to use annotated houses. So there's like large collections of annotated houses to get more training data.
Yeah,
and here
great.
basically what you can do is like construct data sets and then use speaker models to annotate them. And one problem which I haven't mentioned, but is basically how to represent objects. And so if you have these additional data sets, you can use these additionally annotated objects to have better representation.
Yeah, sounds good. Thank you very much. Cool. Yeah, maybe let's thank the speaker again. All right, I guess that now we have a very short break of just 5 minutes. And then at 45, we will go to our second part of the competitions. Basically, we will start 15 minutes introduction of the competition, and then our great winners will present their solutions one by one. And now let's just maybe have a short 5 minutes break, and see you soon.
Please come back at 45. Thank you.
Oh, right. Yeah, let me ping the person who owns the Zoom. So he can.
I can leave, right? Thank you for the invitation.
Yes, yeah, Cordelia, feel free to leave. Thank you.
Okay, bye.
Bye.
Give me 1 minute. I'm just ping the person.
It's not a common.
The yin yang is separate.
Let's resume the part 2 of the workshop. I think next we'll have Defei who will give us an introduction of the challenge as well as the winner. Defei, do you have access? Or you can take over.
So, hello, can you hear me?
Yeah, we can hear you.
Okay, I will start.
Sure.
Hello, everyone. I'm Defei Gao from National University of Singapore, and now I'm gonna move on the challenge part of our workshop. So I will give an overview of the data set and task for the long-form video understanding, and I will then provide an overview of the challenge held in this year. And finally, the most exciting thing, I will announce the challenge winner of this year. And so let's move on to the first part. Yeah, so the motivation behind holding this challenge is that it is a pipe dream that we want models to learn everything by watching videos. So these videos could be about daily activities, like a GoPro or smart glass recording what we did in a day, or instructional videos of how to use some complex devices, or some social medias like vlogs. If model can understand this content, we may build useful AI to assist our daily lives or works. However, the point is that existing methods have achieved great success in understanding short-form videos. These videos could describe one event and the span of several seconds, but stuck on understanding the above videos, which may in several minutes or even longer. Long-form videos here may mean that we need to move from a closed world setting to an open world setting, and from relatively simple recognition to more complex reasoning. So to address this issue, we think the most fundamental question is what tasks should we design to measure the understanding of long-form videos? So actually, cognitive science, some researchers have shown that while human watching long video, we will naturally segment it into chunks without predefined classes. So it may be fundamental for the machine if they can segment the long video into the several segments. And but the reality is that previous models have done a great job in segmentation, but they are all built upon limited size of predefined action classes. So it is hard to existing methods to segment the video without predefined classes. Last year, we took the first step. We proposed a generic event boundary detection task. And there are no predefined event categories in our datasets. And thus, the model needs to output the time steps as long as there is a status change. Could be any action changes or any new object appears. So what's new this year? This year, we not only want to evaluate where is the boundary, but also evaluate if the model knows why it is a boundary. And since our boundaries are not restricted to a fixed class set, so we need to require the model to use a natural language to describe each boundary. So to do so, we construct a new dataset, generic event boundary captioning, where the videos are all from the kinetics. And moreover, we collect the captioning annotations. We don't want the model to just output a general description of what happened at a specific moment. But more importantly, we want the models to dive more into the details, tell us what the subject of the change is. For example, man in the black t-shirt and pants, and there is multiple persons here, but we want to highlight what is a subject that has the status change. And we also want the model tell us what is the status before and after the change happened. So according to the components of an event, which usually involves an object and involves a subject, and the subject may perform some action on itself or on an object, and this action may change the attribute of the thing. So we define five types of status changes. For example, change of subject, action, object, and the scene color, and the mixture of them. And we let annotators to label that these 5 types of boundary, and then label the corresponding caption. And we found that in most cases, the changes are about the action changes. And besides, we found that the vast majority of the videos are in long form with multiple boundaries, and the changes involve various subjects. For example, man, woman, hand, t-shirt, and some object like coat, also something mainly about the same colors. So GBC dataset finally contains 12,000 videos and with 170,000 proposals, and which is comparable to the recent dataset. And more importantly, it is the first dataset to provide boundaries with caption in taxonomy-free events. And let's see another new things we have done this year. We propose a new task towards more practical application. The models not only need to know what happened in a long video, but also we want the model to use information or knowledge in the videos to assist users. Let's take a look at an example. For example, users may encounter some problems in using a new device, for example, a washing machine. And the manual may be too boring or hard to read, so we want a model to answer the user's questions by watching an instructional video. Then the AI will provide a step-by-step guidance. The task is finally formalized as a new form, a affordance-centric, central, question-driven task completion. Specifically, give a visual query depicting what device and what situation the users are facing, and a reference instructional video. This video both contains visual information and a video script. Then we want the model to output a multi-step answer, and this answer can guide the user step by step. For example, first press some button, then press some button, then the work is done. Finally, the task has some unique features, and compare with existing VQA or visual dialogue or some EQA tasks. Our dataset is unique at our videos are mainly about the egocentric video, and more importantly, it is about the usage of devices. So it contains some very abstract concept. And also our questions are not about only about the basic appearance of actions or things or objects, but the function of the devices. And in addition, our task needs to output a sequence of actions instead of just an answer, that's a single word answer or phrase. So these features all requires more complex reasoning paradigm and towards more practical application scenarios. And to evaluate such tasks, we also create a AssistQ dataset which contains diverse home devices. And most of the videos are longer than 1 minute, and those are long form video. And the most of the answer also needs more than one step, so the model needs to complete a very hard mission to get the answer. So after the overview of the data set and task, we are going to talk about the detail of the challenge this year. So this year we held 3 tracks and corresponding to 3 tasks just mentioned. For these tracks, we released the training or wall set for developing the methods, and the teams competed on the test set. For evaluation of track 1, and similar to the last year, given a video, the model is required to output the time steps of boundaries in it. Then we calculate the relative distance between the ground truth and the prediction. Then calculate the FE score as the final results. For the track 2, given a video, and we additionally gave the ground truth boundaries within it. Then the model is required to output the 3 parts of the boundary captions, including the subject, status before, and status after. So for evaluation, we use the commonly used caption metrics, SPICE, Wrangler, and Cedar, to calculate the score of each part, then take the average as the final score. For track 3, given a video and a multimodal query, the model is required to output a multi-step answer. And the output of our multi-step AQTC is quite similar to the multi-round visual dialogue. So we use the retrieval-based metrics to evaluate the predicted answer, including recall, mean rank, and mean reciprocal rank. Here is the most challenge details for further researchers who are interested. And we released the white paper, start code, and hold the QA forum for each track. Yeah, so now let's go to the most exciting part. We will announce the challenge winner. Okay, this year we also have participants across the world, and they are from many famous universities and companies, and there are 33 teams in total. And let's look at the results of a leaderboard of the track 1. Last year winner achieved 0.83 FE score, and this year the participants pushed the best score to 0.86. And I'm happy to announce that the team from the back dance wins the first place award. Yeah, and Tencent and the Tsinghua University win the second place award. And the team from the Nanjing University and System Research and Shanghai AI Lab win the third place award. And congrats to all of them. And also for the captioning track, there is also a significant boost compared to the baseline method. And the top 1 winner achieves 0.74 scores, which is very promising. And we're also happy to announce that also the BackDance and the Institute of Software Chinese Academy of Science win the first place award. And the team from the Southern University of Science and Technology and the University of Hong Kong win the second place award. And the School of Industrial and Management Engineering, Korea University win the third place award. Also, congratulations to all of them. And let's look at track 3. And track 3 also, this is the first year we released this challenge with this task, and there is also a significant boost compared to the baseline method. The top 1 winner achieves 0.4 scores, and it's also a very significant improvement. And because only 2 teams surpassed the baseline, so there are only 2 winners in this track. So the team from the University of Science and Technology of China wins the first place of the track 3, and the team from also National Institute of Science and Technology and Player Inc. Win the second place award. And congratulations to all winner teams, and thanks all the participants. And the technical reports of all winners will be posted on our workshop website. So anyone who is interested can go to there to find their technical reports. So Thanks all. Yeah. Now let's move on to the winner talk. And I guess, yes, first we need to invite the team from the beta dance, back dance to talk about his method. I will stop sharing here.
Okay, can you hear me? Can you see my screen?
Yeah, sure.
Okay. Hello everyone, my name is Ma Xiaoqi, and today I will introduce our SC Transformer++ network in generic event boundary detection challenge at CVPR 2022. Our team have 5 members: Hong Dexiang, Ma Xiaoqi, Wang Xinyao, Li Congcong, Wang Yufei, and Wen Longyin. My talk today is divided into 3 parts: motivation, approach, and experiment. As we all know, the text of JEBD aims to localize the moments that break a longer event into shorter temporal segments. So understanding different event change patterns in videos is crucial for this problem. To tackle this problem, we designed 2 detection mechanisms. For boundaries with drastic visual changes, such as short boundaries or boundaries with illumination changes, the original SC transformer with group similarity is able to handle them well. Features from a newly introduced decoder are used to detect other boundaries caused by action and object change. We also introduced the category call label as an auxiliary supervision signal to further boost performance. This is an overview of our approach. Our approach consists of 5 components: feature extraction, backbone, SC transformer, boundary prediction, category prediction, and the final selection. For the backbones, we use a channel-separated convolutions network as the RGB backbone, and we use the MC3 network to extract optical flow characteristics information. And then the optical flow features and RGB features are concatenated as the input frame features. In this part, we will talk about the structured partition of sequence SPOS, also called module. And this is an illustration of the SPOS. And this part is a key design for the end-to-end model. The orange square is a candidate frame. To obtain adjacent K-frames before candidate frame and the K-frames after the candidate frame, we split the input video sequences into K slices. Each slice is responsible for producing adjacent frames. All video frames can be covered within all K slices and can be efficiently proceed in parallel. Finally, we can obtain all temporal contact frames by repeating K times for K slices, and each frame is represented by its adjacent frames in a local window. And in this section, we will talk about the transformer encoder and decoder. We use transformer encoder to model the structured context information. The output from the transformer encoder is then fed into the group similarity module, which is able to detect boundaries with drastic vision changes. But boundaries with action or object changes are difficult to be learned solely based on feature similarity. To accommodate this issue, we introduced the transformer decoder. The transformer decoder can help extract high-quality features of the candidate frame. The features generated by the transformer decoder and the group similarity are combined and passed to the single class classifier to detect the boundaries. Meanwhile, the features generated by the decoder are also used to compute the categories information of the boundaries in the multi-classifier. And this part is the group similarity. The input features are divided into different groups by channels, and then we calculate constant similarity between each group. As we can see in the right finger, the first row indicates that there is a potential boundary in this local sequence, while the second row shows no boundary in this sequence. Although boundaries in GEBD are defined taxonomy-free, the main category of all boundaries are also provided in the annotation. This category called labels would also be used for supervision signal for boundary detection. As shown in the framework, the category and boundary information are calculated by the single classifier and multi-classifier, respectively. These two branches work in parallel. One is responsible for boundary prediction, and the other is responsible for boundary category prediction. Then we select the max confidence score from these two branches to merge the results. For the post-processing part, we first obtain the boundary confidence scores sequence of the whole video during the inference. To prevent duplicate predictions of adjacent frames, we apply peak estimation technique to the confidence scores. Then a threshold is used to filter out peaks with lower scores, and the peaks with scores higher than the threshold are selected as boundaries. To further boost the performance of our model, we average the prediction scores of several models trained with different architectures and hyperparameters. The settings of different models are listed in the table. And we randomly sample 2,000 videos from Kinetics GEBD validation set to construct a local validation set and use all the rest of data for training. We conduct several ablation experiments to comprehensively understand the performance contribution of the proposed framework. On the validation dataset, the F1 value of the base model S transformer is 0.8312, and the result of the different ablation experiments are shown in this table. And the FE scores of the final ensemble model is 0.8541. We ensemble 12 models with different parameters. Our final result on the Kinetics GEBD test set achieved 0.8649 F1 scores. Positions solely based on feature similarities tend to have high precision, but low recall on the validation and the test partition of GEBD. After our improvements, precision and recall are balanced. And thanks for your listening. Okay, that's all. Thank you. Hello.
Okay, thank you so much. Is there any questions? Or let me see, maybe we can, if you further someone has some question, we can QA at the final. Thank you for your interesting talk, and maybe let's welcome the second place winner to introduce their method.
Okay, I will terminate my share.
Okay, thank you.
Hi, can you see my screen right now?
Yes, okay.
Okay. Hi everyone. So we are the team Camp, and we come from Tencent Interactive Entertainment Group, Common Data Platform Department. First of all, let me express deep gratitude towards the organizers who hold this generic event boundary detection workshop, and it is an honor to represent our team and present our method here. So let's get started. Our model structure is largely based on the contrastive learning approach model provided by the Yangtze CIP Lab, who have won the Kinetic GEBD Challenge in 2021. However, there are still many difficulties in the GEBD task. First, the definition of generic event boundary is highly subjective. Each video in the Kinetic GEBD has manual annotations from different persons with huge differences, like the example on the right. Also, for this task, we cut the video into equal length short sections, let's say 0.25 second sections. And so a 10-second video will have 40 sections. The segment was positive if there is a boundary there and negative otherwise. However, the proportion between the positive and negative samples is highly unbalanced, also like in the example. Moreover, when the model predicts that there's a boundary in the short segment, the prediction can only be made accordingly with only 40 choices, which also affects the F1 score. We proposed various methods to tackle these difficulties mentioned before, and in addition to targeted solutions to the existing difficulties, we also use MAE-based models to solve the GEBD test from different perspectives. Let's first start with the MAE model structure. Recent masked autoencoders approaches have shown state-of-the-art performance on various tasks. MAE developed an asymmetric encoder-decoder architecture with masked tokens hiding a high proportion of the input images. Video MAE proposed the model on video tubes and shown to be data-efficient learners for self-supervised video pre-training. This image here shows our MAE GEBD model structure. Our MAE for generic event boundary detection is inspired by these models. In the pre-training stage, we use the entire kinetic GEBD dataset for the pre-training to get the embeddings, where we mask out 90% of the training data. In the fine-tuning stage, we fine-tune the encoder inherited from the previous stage with these embeddings on the GEBD task. Here we deployed a multi-head training with both BCE and MSE losses, and the results from both are get averaged to get the final output. We use the method named soft label to alleviate the problems of ambiguous labeling and unbalanced samples. As we have presented before, we split the videos into short sections first. Let's say we have an annotation at time t. So the sections represent the 3.5 second will be positive, like here, and others will be negatives. For our soft label method, we allocate each annotation to the two sections nearby according to the ratio between the distances, as shown in this example. So therefore, there will be more weak positive samples in the training data, which partially solve the problem of unbalanced positive and negative samples. And these scores can also reflect the relative distance to the real annotation. The closer the model predictions are to the true annotation, the higher the score it will get. The model will finally provide us a possibility score of length 40 associated with the training on the interpretation side. Instead of find and output the local maximum like the 6.25 here, in the example, we shift the prediction from the gray line to the red line according to the scores nearby. So just like in the equation, as the scores on the right is higher, we move the segmentation to the right to make the prediction more precisely. Meanwhile, we also use the pseudo label to gain more training data for the unlabeled data sets. After the model gets trained for a while, we use the model to make predictions on the test set and then use these pseudo labeled data to train the model again. It turns out that this pseudo labeled strategy can improve model performance both on the validation and test set. The last trick we want to introduce is our segmentation alignment. According to the definition of the challenge, there will not be a segment boundary in the first and last 0.3 seconds of the video. And when computing the F1 score, a prediction will be counted as true positive if there is a ground truth that falls into a plus or minus 5% of the video duration affecting interval around the prediction. In order to make our predicted boundaries to be more efficient, we want the affecting intervals to have overlaps as small as possible. We want our prediction to be at least 10%, which is 1 second in a 10-second video apart from each other, and also away from the first and the last 0.3 seconds of this video. So this trick tends to work no matter what model structure we use in the first place. So maybe you can try this trick on your model and there could be an improvement as well. The last part is our ensemble method. We want to split the data into easy and hard cases, specialize the model on the subsets. We mark a video to be hard if the prediction score curve is flat without much fluctuation. We think that it means the model doesn't know well about where to cut the video. We set a threshold to split the data into two and fine-tune the model on the subsets. So when doing interpretations, the easy and hard test set can also go through two different models as well. Finally, we assemble 20 models from our base model trained with tenfold split and 4 MAE GEBD models with different training strategies. And on the right is the scores we get from each of our methods step by step. We can see that the MAE model has a comparable F1 score with the original model and can help also after the final ensemble. The ensemble gives us the largest improvement, but also notice that the simple segmentation alignment trick here also provides an improvement of 1.1% on F1 score. Our final score on the test set is 85.94 and has ranked number 2 in this challenge. That's pretty much everything we want to present today. Thank you very much for listening. Our code is available on our GitHub page and feel free to contact us through email. Thank you.
Thank you. Is there any question?
Yeah, actually, I have a question. For the pseudo label, can you just provide more detailed information how you use them?
Let me see the pseudo label one. So basically the idea is that we have a small data set for the kinetic GEBD data set, but the kinetic 400 is really large and with a lot of data without the labeling, right? So our idea is sort of like we want to use more samples from the unlabeled data to our training to make improvements on our final score. But in our plan, how to say that? Like we finally, because of the time limits, we only use the test set to do the pseudo label thing. So basic idea is that we use the training data to train a model for a while, and then use this model to make predictions on the test set. Because we kind of have different versions of the models, and they will also give different versions of the prediction on the test set. And then we use this predicted results of the test set called pseudo labeled data and put it back into the training set, and then train the model again, and we will get a new version, improved version of the new model. Yeah.
Oh, okay. Thank you.
Okay, thank you. So I think let's move on to the first place winner for the track 2. So if someone also has questions, we can discuss at the final QA session.
Can you hear clearly?
Yes, sure.
Okay, thank you. And let's begin. Hello, everyone. I'm Gu Xin, a PhD student at UCAS. I will represent our team by caption to represent our work in track 2. Our team has 6 members: Gu Xin, Ye Hanhua, Chen Guang, Wang Yufei, Zhang Libo, Wen Longying. Our method is called dual stream transformer for generic event boundary caption, and I will introduce it in 3 parts including our motivation, approach, and experiment. Track 2 is named generic event boundary caption, which aims at capturing the generic event boundary caused by status changes in videos. The task is more complex than normal video captions. It requires understanding not only the state of the event split boundary, but also the 2 states before and after the split boundary, and how they change. Through our group analysis, we have summarized several challenges in track 2. A lot of information are contained in each video. Therefore, the first thing we need to figure out is a way to represent video features. For these extracted features, an overall algorithm is needed to fuse them in a useful way to produce a global view of the event. In addition, each boundary contains 3 states up on time. How to make the model distinguish them would be a crucial problem. For these problems, we designed several solutions in a target way. For the first question, we utilize 3 pre-trained models to extract the video features from different granularities. As in the second problem, we particularly design a model termed as dual string transformer to not discriminate representation for boundary caption. Finally, to distinguish the 3 states of the boundary, we set the corresponding states token for each state. Next, I will introduce our approach in detail. The overall structure of our approach is shown in the figure. The model main consists of future extraction model and the future encoding model. The first step is to extract the multimodal features. Next, we encode the features by 2 branches to use them to generate a description text. In the future extraction model, we use 2 frames per second for each video. In order to get the best representation of the video features, 3 different feature extractors are used to extract video features. The first one is the clip. Clip extracts appearance feature, and the next is the video swing. Video swing extracts motion features, and we also use the region features. Region features is extracted by the faster CNN. Meanwhile, we use the globe model, which has been pre-trained on Wikipedia data to encode text information, including wedding type and the generated video caption. And now we get 4 kinds of model information by feature extraction model. To fuse these features in a global form, we design a dual string network architecture based on transformer. The input to the global string is motion feature, appearance feature, and word embedding, while the input to the local string is region feature and word embedding. The self-attention in the model is built for future alignment, while the cross-attention is built for future interaction. To verify the rule of the different models and the features, we perform ablation experiments. The experiment leads to the following conclusions. First, the fusing of different video features helps the model understand the video. Second, video type information can help the model to distinguish different states when generating description. According to the table 2, the experiment results show that our proposed method performs greatly on the generic event boundary caption. That's all the information about our method. Thank you for listening.
Okay. Is there any question? So if no one has a question, we can move on to the next talk. Let's welcome the second place winner of the track 2 to illustrate their method.
Hello, can you hear me?
Yeah, yes. Oh,
Okay.
wait.
Okay, I will start.
Yeah.
Hello, everyone. I'm Jinrui Zhang, an undergraduate student from Southern University of Science and Technology. In this talk, I will briefly introduce the technical details of our solution to generic event boundary captioning challenge 2022, namely exploiting context information for generic event boundary captioning. Our team members are from SUSTech and Hong Kong U. We start our talk by introducing the motivation of our method. Generic event boundary captioning is a task aiming to generate multiple captions describing the events for the given time boundaries. Intuitively, context information could benefit event understanding. Specifically, The event boundaries subjects of the same video are highly likely to be related. Some events even share the same subject. And there are some interactions between events. For example, an event may be the cause of another event. However, the official baseline method only processes single boundary at a time, which limits their ability to utilize context. To better exploit the context information, we design a model which takes the whole video as input and process multiple event boundaries parallelly. Our boundary captioning system can be described in the following pipeline. We first encode the video to visual features, and then we exploit in context information that are related to each event boundaries from the whole video. Finally, all event boundaries captions are generated parallelly. Here is the overview of our model. Our model is based on the transformer architecture, where transformer encoder is used to encode visual features, and the transformer decoder with the caption head is used to generate captions. To better exploit the spatial temporal information, we use multiple pre-trained models to extract various features. The used models are as follows. CLIP pre-trained on 400 million web image text pairs, and Omnivore pre-trained on ImageNet 22,000 are utilized to extract frame level features. To facilitate the batch processing, the interpolation strategy is performed to resize the temporal dimension to a fixed number. To further get the better representation of frames, we use multiple temporal convolution layer to generate multi-skew features. We also use VIN-VL to extract region level features. It is pre-trained on 4 public data sets, include COCO, OpenImages v5, Objects 365, and VG. All frame level features are fed into a deformable transformer encoder to further capture the temporal interaction by self-attention. To model the context information and get event level features, we first construct event proposals from event boundaries. Because three different kinds of captions focus on different time periods relative to the boundary, we construct 3 different proposals for 3 caption generation. And this is described in the top right figure. The proposals are first used to query region level features to capture object cues. Then the frame level features are queried to gather the context information that relevant to each event. The output of transformer decoder can be regarded as event features. They are further fed into a caption head to predict the event captions. We follow PDVC to use LSTM with deformable soft attention at the caption head. In our experiments, we use the official provided 4 training set. We first train 3 models with cross-entropy loss. Then we fine-tuning the 3 models by self-critical sequence training, which is a reinforcement training strategy for caption generation. Here, we list some experimental results. As shown in the first 2 lines, our method achieves about 33% improvement compared with the baseline method, which demonstrated the effectiveness of context. We found that the combination of 2 features perform better than single feature. Region level features could clearly yield the performance gain, especially for the subject caption generation. We use self-critical sequence training to optimize the CIDR metric, which could further improve the performance. Our final score on test side achieves 72.84. Okay, thanks for your listening.
Okay, thanks. Hey, Sarah, any questions? Okay, so let's move on to the next speaker. Guess the first place winner for track 3. Can you hear me? I think You are muted. I can't hear you. Still cannot. Or maybe you can rejoin the Zoom. Hello. Sorry, Shui, I still cannot hear your voice. So maybe we can let the next speaker first talk about their method, and then you can rejoin the Zoom meeting. Is that okay? You can chat on the chat room.
Let's
Should we?
speak through this one. Okay.
Okay.
Can you see my screen? Okay.
Yeah, sure.
Okay, sure. Hi, I'm Henry Kim, and I'm going to report our second place solution for the track 3 of Lottery Challenge this year. Now, Team Pilot AI Context Lab had members from UNIST AI Graduate School, Jongwon Kim and Jongwon Kang, and also from the Pilot Incorporation, which is the exponentially growing AI ad tech startup, mainly researches about video understanding and contextual marketing. And finally, we have our advisor, Taehyung Kim. So the newly introduced AQTC task aims to help users operate machines in the real world from an affordance-centric perspective by answering users' questions such as, how can I change the light intensity? Then an AI agent that learned from instructional video would answer, the user like to change the light intensity, don't press the button 0. However, this task has several difficulties. First, there are multiple step answers in each question with multiple choices. And also the buttons may appear different for each step because the instructional video have egocentric movement. Lastly, it deals with multiple modalities of text and images for video, sans scripts. So we have our model here, and we have 3 main components. And in the first part, the feature extractor encodes the input data using vision transformer and BERT following the baseline. And next, we have context grounding module, and we focused on designing this part so that the model could understand the question better. And you can notice that we concatenate 4 different features in the later part in this model, and I'm gonna explain these features in detail. So we first calculate the feature T using the series of cross-attention operation, and we decided how to combine those multiple features by considering the nature of features. So for example, feature I and A, which refers to user image and answer text, both describes about the button information, and we assume those to be semantically relevant. Next, we generate the feature 3, and it is obtained by multiplying the average attention rate and the output of cursor attention with script and video features. And finally, we concatenate 4 features and put into NLP to get the output feature. And we also explored using other features in the position of feature I and A, but it turns out that using both were the best. And we assume this is because those features are most relevant features to the answer. And in the end, we have step networks, and we use GRU following NLP with softmax following the baseline. So the assist-Q data set comprises of 100 samples, where 80 samples for training and 20 for the test. And we split the training set by 60 to 20 to generate a validation set and tune the model and hyperparameters. Afterward, we make all use of training samples to train the model. And we also summarize the number of buttons in the training set as the right figure, and could observe that there's imbalance in the number of buttons, where the half of the samples had less than 10 buttons, while between 11 to 20 and over 20 was 29 and 12 each. So when we generate the validation set, we try to make it have balanced number of buttons. And with this observation, we tested our best model's performance on different tests of set, and could find that the number of buttons had large impact on model's performance. And as shown in the left table, the model could achieve higher score on samples with few numbers of buttons, especially high for the recall at 3 and mean rank. Meanwhile, performance degrades drastically as the number of buttons gets bigger, except for MRR. From this result, we argue that the AQTC task gets demanding as the number of buttons grows, and also suggest that the model would gain performance by having ability to handle the samples with lots of buttons. And it can be done in the future work. Finally, our best model could get competitive scores, second place for the average rank, and the first place in 2 evaluation metrics. Okay, that was all for my presentation, and thank you for listening.
Thank you. Is there any questions?
Hello, I have a question. Can you hear me?
Yeah, I can hear you.
Yeah, hi Kim, thanks for your presentation. I wonder how important do you think the attention in this task? Specifically, any ablation study about your cross attention model?
Oh, so you are
yeah.
Is about
yeah.
Right? Okay, so I think our modification is mostly about modifying.
Oh, yeah.
And just by that we could like have better performance, distinctly better performance, and we speculate that it is because model can learn better by better feature mapping, and yeah, it is quite important.
Oh, okay, I got it. So yeah, that compared to baseline, that's your improvement, right? Okay, thank you.
Okay, thank you.
Yeah, maybe Shui, you can try if you can work this time. Share your screen. Oh, is there any questions from other audience? It's okay to ask our speaker. Is Shui here? Yeah, I see you. So Hello? No, I guess I still can't hear your voice. Can you see another audience suggestion? I think you need to switch the mic. There is a button, audio button, and you can switch you speak or you can select a microphone, different microphone. We still cannot hear your voice, so you need to tune your microphone. Okay, I guess so. If that situation, maybe we'll ask you to upload a video.
Yeah.
Yeah,
Maybe
so
we upload a video, then
you can upload video and send the video to us, and I will upload it on our workshop website.
yeah. That doesn't matter.
Okay, I think that would work. So let's move on the QA session. If there for all the speakers, if you have some questions, you can ask all the speakers here. I guess all speakers are still here.
Hello, may I ask a question to the champion or the first place winner of track 1?
Yeah, sure.
Yeah, so I have a question related to your model. So I wonder if you utilize any pre-trained model in your solution, and do you have any ablation of how these pre-trained models affect your performance?
Actually, for the RGB backbone, we try different pre-trained models, especially for the we tried the latest video swing transformer, but it's actually even worse than the previous backbone, such as ResNet or CSN. So we so we basically try different a whole bunch of networks and find the CSN works the best.
So what is the best pre-trained model you used in your experiment?
CSN.
Okay, thank you.
Yeah, I believe CSN there's a version that pre-trained on the Instagram 65 million, and then Kinetics. That one worked the best.
Okay, sounds great. Thank you.
Mm-hmm.
Is there other questions?
Maybe I have one more question for the winner from track 3.
Yeah, track 3, I guess.
Maybe the second place winner, because Suri cannot hear his voice due to some technical issue. So I wonder for the step networks, how you handle the question with different number of steps to tackle different question.
Oh yes, like you said, we have different steps for each sample.
Sorry, I cannot hear you clearly. Maybe you can.
Can you hear me clearly?
Yes. Now better.
Yeah, it's right. Like you said, we have different steps for each sample, and in the baseline, following the baseline implementation, we calculate loads and everything with every step, so that we can bother from the varying sequence, the sequence length.
Okay, I see.
Thank you.
Okay, thank you.
Okay. Is there any other question? Okay. If there is no further questions, I will give a closing remark. I guess we can wait 1 or 2 minutes for somebody want to ask speakers for more details. And if there is also still no questions, I will go to the closing remark session.
Final call. Any questions for speakers? If not, I think you can do the closing remark.
So so if there is no questions, I will go to the closing remark. Yeah, so thanks to all audience, online audience and offline audience for listening. And thanks to all the keynote speakers for their interesting talks, and they provide valuable insights from various perspectives: model architecture, self-supervised learning strategies, and how to utilize multimodal information in learning in long-form videos. And thanks to all who participated to our challenges. You advance the research on long-form video understanding. And I guess more specifically, the participants in all tracks significantly boost the SOTA results and propose many interesting training strategy, model architectures, and video representations. And hope next year we can provide more interesting data sets or tasks with more interesting applications. I think this year we focus on more interesting application, for example, usage of devices. But next year we want to assist persons or users in more general scenarios like playing, working, eating. So we can have, let's build more interesting applications, some fancy models. And also we want to propose more powerful baselines, for example, designing more powerful fine-tuning strategies to use pre-trained models on large-scale dataset to boost the performance on small dataset, for example, in our AQTC. In addition, we also want to construct a much larger dataset than maybe facilitate the researchers to train their model to diagnostic their methods. I think that's our next year's plan. And again, thanks for you participating in our workshop for all audience. And I guess we will upload all the videos to our workshop website. And if you have further questions, I'm very happy to hear your questions or suggestions through emails or QA forum of our challenges. So I think, yeah, thank you all the audience. And hope we can see you next year. Yeah.
Thanks all for coming.